Good afternoon, everyone. Thank you for being here. My name is Angela Sokan, and I'm presenting this work today, a low-rank factorization in FlauBERT model for energy consumption reduction, with the submission number DAP 2025-58. My colleague Vincent Courboulet and I are both researchers in France working on sustainable AI at CERAD, ISEP School of Engineers at Angers, and La Rochelle University. Today I'll be sharing our recent work on energy efficient natural language processing, especially focused on FlauBERT, a powerful French language model. Explore how low-rank matrix factorization can decrease the energy footprint of this model during inference without sacrificing performance. Our contribution addresses this question: how can we make AI not only intelligent but also sustainable? And let's begin with the motivation behind our work. In recent years, NLP models have become significantly larger and more powerful. Models like BERT, GPT have transformed how we process and understand the language, but this progress comes with a cost. These models are also resource intensive, especially during inference, which is the phase when the model is used in real application. And that's a key point I'd like to emphasize. In most studies and discussion, the focus is often on the training phase because it's computationally heavy and easy to quantify. But training typically happens once. Inference, however, happens millions of times in real-world use cases. Unfortunately, the inference phase is understudied and rarely optimized. Most companies don't measure or manage the energy consumption of models in production. This is why our work focuses not on training, but on reducing energy usage at inference time, where the long-term impact is far greater. Do you know that inference, not training, dominates energy usage in real-world deployments, often accounting for more than 90% of model lifecycle energy? To explore this problem in a real-world setting, we choose to work with FlauBERT, a French language model based on BERT architecture. It was trained on a large and diverse French corpus over 71 gigabytes of high-quality text, including Wikipedia, news, novels, and more. It's known for being one of the most powerful French NLP models. It's very used, but this model comes with a significant computational and energy cost. Its architecture includes millions of parameters and multiple transformer layers, making it difficult to deploy efficiently on low-power devices or in high-load cloud environments. So we ask the question: can we compress this model in a way that reduces its energy usage without sacrificing performance? And how can measure that? That's the core of our case study, applying low-rank factorization techniques to FlauBERT and analyzing the impact on energy efficiency during inference. So, why focus on model compression? Why does it matter in the context of energy-efficient AI? First, because large language models like FlauBERT are over-parametrized. We can reduce their size without a significant loss in accuracy. By compressing this model, we can achieve several important benefits: lower energy consumption at inference, faster response times, reduced infrastructure cost, deployment on edge devices, and beyond the technical benefits, Compression aligns with broader sustainability goals. It supports green IT practices and it reduces the energy footprint of AI application. And it prepares us for future regulatory frameworks that may impose limits on digital energy consumption. In short, compression is not just a technical trick, it's a strategic solution for building responsible AI systems. In transformer models like FlauBERT, many of the largest weight matrices are used in the feed-forward and attention layers. These matrices can have 10 or hundreds of millions of parameters. However, we often find that these matrices are redundant, meaning they contain patterns that can be approximated with fewer components. With low-rank factorization, we replace a large matrix with the product of two smaller matrices. This reduces the number of parameters, computationally cost, memory footprint. The goal is to maintain the same overall structure and functionality of the model, but make it lighter, faster, and greener. This approach is modular, doesn't require retraining from scratch, and can be integrated into many transformer-based models. In our methodology, we applied low-rank factorization to just 6 of the 12 attention layers in FlauBERT. We did this selectively because compressing all layers led to a noticeable drop in accuracy, so it was important to preserve the most expressive part of the model. Uniform compression across all layers was avoided because that would have resulted in overcompression, efficient but at the cost of accuracy. We started by identifying the linear layers in FlauBERT, special in attention and feed-forward components, and applied low-rank decomposition directly to their weight matrices. We experimented with different rank values, which control how much we reduce the size of the matrices, from light compression to more aggressive versions. And after compression, we can make a fine-tuning or not. It depends on your use cases. And we tested the original and the compressed models to accurately assess energy consumption. We use Power API, a fine-grained open source power monitoring framework developed in France. Power API allows direct measurements of the energy used by specific process, such as the Python process running FlauBERT. Low-rank factorization helps make NLP models greener by reducing their size and the number of operations needed. This leads to faster inference and significantly lower energy consumption. And the key advantage is that the model still retains the most important information, so performance is preserved while making the model much more sustainable. For our experiment setup, we used the Allociné dataset, which includes 200,000 labeled French movie reviews. This dataset is widely used in sentiment analysis benchmarks. We evaluate the impact of compression. We compared the full model against its low-rank factorized variants. For measuring energy consumption, we relied on Power API combined with the SmartWatts module, which provides real-time CPU level energy tracking using the REPL interface. Our tests were executed on a Lenovo server equipped with the two Intel Xeon CPUs. We ran inference in batches using 100 samples per loop, repeated over 1,000 iterations to ensure statistical robustness. Importantly, we avoided overcompression by applying low-rank factorization selectively to 6 attention layers instead of all 12. This ensured we preserved model expressivity while still achieving meaningful reduction in energy use. Here we have an example. One matrix after applied low-rank factorization is reduced at 94%, but for entire FlauBERT model, we obtain a reduction of 10%. This plot shows the energy consumption of different versions of FlauBERT measured using Power API over 100 inference runs. The red violine of the left is the base model, is the original compressed model, and as we see, it consumes the most energy. Now let's look at the 3 compressed version. LR5 is the most aggressively compressed with a very low rank. It consumes the least energy, but the distribution is wide and irregular, which indicates instability and potential performance loss. The second one, LR20, is a more moderate compression. It still saves significant energy compared to the base model, around 25–30%, but with a tighter and more stable distribution. The last one, LR30, is slightly compressed. It's closer to the original in terms of accuracy, but uses slightly more energy than LR20. So LR20 offers the best trade-off, energy efficient yet performance stable. Reducing the number of operations like max sounds like a good way to save energy, but it's not that simple. Energy is also used to move data, especially when loading weights from memory into the processor. When compression is too aggressive, the model's memory access becomes inefficient and scattered. This causes more cache misses, and the CPU often waits instead of working efficiently. As a result, energy savings plateau, and we even see performance drop. What we found is that moderate compression, especially in attention layers, gives the best trade-off. It keeps the model light and efficient without hurting accuracy and avoids wasting energy through poor hardware utilization. So, the measure is, don't over-compress, compress smartly. This bubble chart shows the trade-off between accuracy, energy consumption, and model size after compression. The red bubble, model base, it has the highest energy use and largest number of parameters. The blue and gray bubbles represent compressed models. They use less energy, have fewer parameters, and maintain good accuracy. Takeaway: one of the compressed model, blue, hits a sweet spot. It's accurate, energy efficient, and compact. And this visual supports our point. Smart compression gives big energy savings without sacrificing performance. As AI models become widespread, it's no longer acceptable to ignore the energy footprint, especially during inference, which accounts for the vast majority of usage. First, we advocate that AI systems must systematically report energy metrics, just as they report accuracy or latency. Second, compression-aware deployments should be standard in enterprise pipeline. Techniques like low-rank factorization can reduce energy use by over 25% with minimal impact in accuracy. To assure accountability, we propose adopting a metric like energy reduction ratio, which expresses how much energy is saved compared to the original uncompressed model. By adopting EU Green AI, researchers and institutions can help reduce the carbon footprint of AI while still advancing. So, it's not about compression at all costs, but smart, measured optimization tailored to the deployment context. To conclude, I'd like to highlight three key takeaways. First, energy efficient must become a core AI design goal, not something we think about after the fact. Our work showed that low-rank factorization is a practical and effective approach, saving up 25–30% energy, all without compromising performance. We demonstrated this on FlauBERT, a widely used French NLP model, and validating it under real inference conditions using Power API. And most importantly, promote energy-aware AI design, not just in research, but in procurement policies and enterprise systems. In short, we believe that energy efficient should be a core AI performance metric, not an optional bonus. As we look ahead, our future work will focus on four key directions. First, we're exploring a hybrid compression approach, combining low-rank factorization with other methods like quantization. This can further reduce the memory footprint and computational load, especially in environments where both model size and precision matter. Second, we want broader model coverage. We want to apply our method to multilingual and domain-specific models beyond FlauBERT. Third, we plan to deploy and benchmark on RAM-based edge devices, which are increasingly common in mobile and IoT systems. And finally, we advocate for a standardized way to report energy consumption of AI, special for inference. Tools like Code Carbon or Power API or other energy consumption tools could be integrated into pipelines so developers can measure and optimize the energy footprint of every model. One final note, while compression is powerful, overcompression can harm both accuracy and standard hardware utilization. Our goal is to find the right trade-off where sustainability doesn't come at the cost of reliability. And thank you very much for your attention. And we'd be happy to answer your questions and discuss future collaborations. Have a good day.